As you enter this California National Park, you can't help but be overwhelmed with the dimensions and the magnificence of this park. With walls all around you that tower high above the valley floor, we're going to talk about some of the history and how this place came to be what it is today. Okay, so today we're taking you to a place of fire and ice. Well, it's not really fire and ice, but a lot of it was formed by magma, and then ice played a big role, right?
Yeah, lots of glaciers pass through this area.
So where do you think we are? How about Yosemite National Park? John Muir is often regarded as the father of the national parks, and he's responsible for bringing these treasures to the attention of Congress. And because of his efforts, in 1890, Congress established Yosemite as a national park. However, it didn't include Yosemite Valley. That still remained under state control. It wasn't until he invited Teddy Roosevelt to spend 4 nights in the wilderness, and through Teddy Roosevelt's influence, Congress then appropriated Mariposa Grove and Yosemite Valley to the park, and that was in 1906. So now let's take a look at what's so special about this park in particular. Let's set the stage for our setting in the Jurassic and Cretaceous, where we had a subduction zone, the Farallon Plate, on the west coast of North America. And as this ocean crust went down, it created a melt beneath the continental crust that rose to the surface. Now, the amount of material that came out of the melt was truly phenomenal. A lot of it made up the Plutons that we see in Yosemite, but overall, with several hundred possibly of these Plutons, this made up the whole batholith of the Sierra Nevada. After the Cretaceous, some of this magma made it to the surface as part of the volcanics that we see just outside the park in the higher elevations. Essentially, these volcanic rocks from about 20 million to 5 million years ago essentially buried the granite below. It wasn't until the numerous glaciations that revealed the granite below. So let's take a moment to review just what exactly is in granite. And if we take a close-up look of a piece of granitic rock, and there are different kinds here, but the main thing we can notice is that there are some dark minerals, which are probably hornblende if they're slightly elongated. They could also be biotite, but predominantly around here they're hornblende. And then we have a whitish mineral, which is our potassium feldspar. And then we have a clear but slightly milky grayish type mineral, and that's our quartz. So each of these minerals can be found in different percentages, and they contribute to the different rock bodies, whether it's granite or diorite, which tends to be darker, as you can see here, or even a granodiorite, which is somewhere in between. Now, there will be times when you come across some large crystals in your granite, and this reflects the cooling rate. So the larger the crystals, the more time they had to grow. And then they're usually embedded in a matrix of smaller or finer crystals that cooled quickly. Yosemite National Park is home to about 35 different intrusions that went from about the Jurassic to the late Cretaceous, or about 125 million to 85 million years ago. Now, the whole Sierra experienced probably over 200 intrusions during that same period. So this is part of the larger scale batholith. And behind me is just one of many in Yosemite Valley. So we've had about 7 intrusive suites during this period. Now, an intrusive suite corresponds to a magma source that is a common root to a number of Plutons. So you might imagine a magma chamber that has a number of roots or a number of veins or fingers that feed up to the surface, creating several Plutons. And we know this through the common chemistry. We look at the sequence of events through what we call cross-cutting relationships. We also look at the radioisotopes, or we date these rocks. Now, when we talk about these cross-cutting relationships, we're looking at things that will help us understand the sequence of events. And in this case, when we look at El Capitan, there's a nice dark splotch. And that intrusion of diorite came into the granite which is the surrounding lighter material, a lot later. The granite was in place probably about 92 million years ago, and the diorite came in later. Now, just in that region, you also have white veins, and those are aplite. That's another intrusion that came after the diorite. So you see how we can start to build up these relationships and sequence of events, even though we may not always know the exact dates. And this is what we call cross-cutting relationships. It's not uncommon to see some foreign material in the granitic rocks. These things can be as small as your hand or even tinier. They're usually pre-existing material that the granitic rock pushed into, or it could be other intrusions or Plutons that were in place where the magma has pushed its way through and incorporated it into its new melt. Many of them are somewhat rounded, which gives the impression that they've been pushed around a bit in the new magma, which is the lighter material, and these guys came from pre-existing Plutons. Quite often these xenoliths have a different color or texture, and so it really tells you something about the other material that was in place beforehand. It had different chemistry, which is not uncommon or unexpected. Next we have joints, which are essentially fractures in a rock, and this can be created in a couple of ways. They can be tectonic, which means that the rock body has undergone some kind of large-scale deformation, and so the stress when it's released results in a fracture. There can also be exfoliation joints in our rocks, and these again result from the removal of stress from a rock body, but they're also oriented in a slightly different direction. We'll talk about those shortly. As far as the tectonic stresses, if we look at an image of Yosemite from above and the contours, we can see that there are a couple of sets oriented to the northeast and southwest, as well as to the northwest to the southeast. Now, in these sets, quite often the rivers will align themselves and work their way in. It's a plane of weakness and an area where erosion can take place readily.
We're here at the foot of Half Dome in Yosemite Valley, and the features you're seeing behind me, some of the fractures and slabs of rock, are the result of a really interesting physical weathering process called exfoliation. And the way this forms is when the magma solidifies at depth, kilometers down within the earth, there's a lot of pressure on top of it. And then once the material on top of that magma chamber it gets eroded away and the structure becomes part of the Earth's surface, it is no longer being confined, and it expands a little bit and cracks in different layers, and the layers start peeling off. And this is much like an onion. So if you peel an onion, you'll see that it comes off in layers, and that's exactly what's happening to these layers of rock. Because of the expansion, there are a set of fractures that are in this direction that are perpendicular, and there are also a set of fractures that are parallel to the Earth's surface, and it makes this rock peel off in slabs.
Here's another example of how exfoliating joints are parallel with the undulating surface of clouds' rest.
So this is a super interesting outcrop. It's an outcrop of granite here in the Sierras, about 80-million-year-old granite. And the way it's weathered is really characteristic of granite. So characteristic, there's actually a word for it. It's called grus. And as you can see, if you look at the rock, that the darker minerals that are more susceptible to weathering have eroded away, leaving some of the more resistant minerals. And the end result is this kind of rubbly stuff, almost like little BBs. It's really tough when you mountain bike on them. So if you look closely at the rock outcrop, you notice that it's not all eroding at the same rate. There are certain areas that seem to be more resistant to erosion that are kind of jutting out from the rock, and that's probably due to the slight difference in the minerals there.
See how crumbly that is?